So the thermometer, what we end up having is we have a large cylinder and a little tiny cylinder like this. We changed it. Oh. But why didn't I do that? So we have like how old thermometers work is we have some mercury down here. They've now changed it and got away from mercury. And we have this little tiny column right here. As we heat the mercury up, it's able to expand. So as you heat something up, like water, whenever it freezes, it expands. Water is different than other objects. Most objects like expand and get bigger as you heat them up and cool down. So as you heat up this mercury or whatever liquid's inside of it, this is going to go up and down based on temperature. The hotter you get it, the higher this is going to climb up. We then just put tick marks everywhere and measure standard temperatures. So we put this in some ice. We put a 0 on wherever it's at. We put it in boiling hot water. We mark that 100, and that's the thermometer. And we go and do line separating it. For an analog thermometer, we have to wait for this to expand. So we're kind of delayed behind it, right? It doesn't expand immediately. We have to wait for it to reach that temperature and do it. It's bad compared to using something like a digital. So this was the data we got yesterday. For the other class, I used about 3 times the ice, and I also turned on magnetic stirring. I put a paper clip inside of it so it stirred the water. We got a whole lot better results for the beginning. This was when the ice fell over and then the temperature went up. I started reducing because the problem with stirring it while it's heating up is we're constantly mixing in cool air down into it, so it cools it off a whole lot faster. I think right here I completely turned off stirring, and it never actually made it to 100 degrees because it started boiling the moment I turned off stirring. And remember what I said, when it starts boiling, the faster, hotter particles are going to escape and never leave them behind the cooler, which is why the temperature of the water really didn't reach 100 degrees. If I could have trapped it in there better, it would have reached 100, or if I kept it on there longer. But today, we'll have a quiz. Don't worry. I'm going to let y'all work on it by yourself right now. And in about 15-20 minutes, we're going to do it together and compare and see how you do. Mercury isn't really that cancerous. So it's toxic. It's poisonous and toxic. Some types of mercury is carcinogenic, but it's mostly poisonous, extremely poisonous. Like one of the most dangerous chemicals in the entire world is actually a mercury-based. If you take a single drop of it and have 5 layers of gloves, you have about a half a second to a second before the mercury goes through all 5 layers and kills you. It gives you a lethal dose. You'll die in the next week. Yes. So they have to wear gloves over gloves over gloves over gloves. And if one tiny drop splashes on the gloves, they have to quickly take off your gloves, as it'll soak through the gloves. So again, this section is broken up into two parts. I don't expect you to know what heat of fusion and heat of vaporization is. But I want to see basically how well we are doing on understanding the phase diagram. I will say heat of fusion refers to freezing. Heat of vaporization refers to vaporizing. Heat of fusion is also melting too. Melting, freezing. Heat of vaporization refers to vaporizing, boiling. There's a front and a back. But try your best. Again, I'm going to go over the answers here in a second. That is because Miss Erica printed it one-sided on two pieces of paper. Make sure they're different. I was wondering why it looked way more than 12 copies. It really shouldn't take 5 or 10 minutes to answer, I think.
Coach B, did you go to Coach Cameron's classroom, Coach Boyle? Did you come to Coach Cameron's classroom?
Who's still working? Everyone good? Let's see how well y'all did. So, in order for something to freeze, we have to lower the temperature, right? So, if we're starting at a high temperature and we're decreasing our temperature with time, that means that we have to be starting with like a solid or a liquid, and we're changing downward to something. Or we're starting with a gas, plasma, and we're going downward into a solid. So the flat portions refer to phase changes. Oh, sorry. So the flat portions refer to phase changes because temperature doesn't change during a phase change. In real world, there's multiple different oh, actually, before I continue and talk about this, there was a so this is only like 44 seconds, and this is a time lapse. So this is with a digital thermometer. So he's heating up the ice. It started at like -10. If we had a digital thermometer, look how much clean his graph is. Heating it up. We do see that slight change right here, but look how sharp it is. Look how much the temperature really isn't changing either. Yes. That's because it dropped down and some air rushed in and changed it up. But I want to show that if we had a better thermometer and we used way more water, a digital thermometer works totally different than an analog one. Digital one is more precise. We get a way better graph. Yes, that's why I put a request for one. $100 for the one I want. The one I want is wireless, so that I can bring a laptop in and set it up, and then we stand back and do experiments without standing next to it. And because I can't really I don't want the laptop blocking it. I don't want wires too coming near it. Yeah. So these are the phase changes. We see that there's 2 phase changes, and we only deal with three phases in this class: solid, liquid, and gas. The one at the lowest temperature, again, temperature only changes when it's only in a single phase. The lowest temperature has to be solid. The middle temperature has to be middle slope has to be liquid, and the top one has to be gas. So, which letter represents to the point where the material begins to freeze? So, freezing is when we turn into a liquid and a solid. We're starting to freeze right here. So, this is the freezing phase. We're starting to freeze. So, you should have got D. Everyone get D? I'm seeing some erase marks. It says, which letter does it begin at? It begins at D. So at this point, we have ice starting to form around the sides. And at this point right here, assuming expanded, the whole thing is ice. It's only D. That's the point at which it begins. And it says which letter, not which line segment. Uses section actually down there. At what temperature does the material boil? So it's condensing right here, right? It's turning between a gas and a liquid. The condensing point is the same as the boiling point. So if we come over here, if we run this in backwards, we'd be heating up the solid, it'd be going in reverse. So this would be 60 degrees, or unit is Celsius, so 60 degrees Celsius. I'll give proper definitions for these later. So remember, whenever you do a phase change, you're either gaining potential energy or you're losing potential energy, right? And heat is a combination of kinetic energy and potential energy. So whenever an object freezes, it's going to release some heat. So how many minutes? So this question basically says, how many minutes does it take for the object to freeze? Because when you freeze, you're going to be giving up some potential energy, right? So this would be from here to here. So from 15 minutes to 20 minutes to 5 minutes. Again, I haven't covered heat of fusion, but I did give you the hint that this was freezing or melting. So if you go from 0 degrees Celsius water, if you go to 0 degrees water to 0 degrees ice, in order to do this, you have to release some energy, because this is an exothermic. I showed you all the super cooled water, didn't I? So when you take super cold water, you have water that is at negative 10 degrees Celsius, for example. And if you bump it, what would happen is it will turn into ice that might be at negative 5 degrees Celsius ice. So here we're not, literally the action of it freezing causes a temperature change. And the reason the temperature changes is as this is going from liquid to ice, it actually releases heat. It releases heat. And that heat goes into warming up the ice. So the action of actually going from liquid to ice actually releases heat into the environment. At point D on the graph, the material is at what phase? So it's just about to start freezing, so it would be liquid. At what temperature will the gaseous phases condense? Well, this is also 60 degrees. So condense and boil are the same thing. At 10 degrees Celsius, what physical state is the liquid? So coming over to here, at 10, it is a solid. What section of the graph represents the cooling of the liquid state? So C to D. What section of the graph represents the heat of vaporization? So remember, this is the heat released during vaporization, i.e. boiling, or condensation, when it's condensing. So B to C. And this is so I should say this is the heat released. This is the, let me rewrite this. This is heat released during condensation, and this would be heat gained during vaporization or boiling. This is the proper definition of heat vaporization. It either refers to the heat gained during vaporization or boiling, or the heat released during condensation, or heat released or lost. Heat lost during condensation. Again, we're not going into calculating the actual energy yet. So I'm not focused on heat of vaporization and heat of fusion. That's not on the test. You don't really have to memorize this yet. But once we get done with this, we will be actually calculating that. Does anyone want to go back and take a few minutes to correct 1 through 5 on the next page? Alright. See if you got it now. I'm doing this so I let y'all do it by yourselves. Critical thinking skills. So whenever I look at these diagrams, I start out with the changes in phases. So this is going to be a phase change, the flat portion, and this is going to be a phase change. So we know that solids exist at the lower temperatures, right? You can't heat something up and make it a solid. Bad analogy, because technically if you start heating up honey, you'll eventually burn it. But that's actually because you're boiling out all the water. But normally, if you heat something up, it's not going to turn back into a solid. So the lowest temperature of the line is going to be your solid. Your middle one is going to be a liquid. And your highest one is going to be a gas or a vapor. So going from solid to liquid is melting. Going from liquid to gas is boiling or vaporization. So it says the substance is completely vaporized at the end of which line segment? So at the end of M. So here it's still a liquid. Here it's fully a gas. And here it's transitioning. It's part liquid and part gas. So it doesn't finish turning into a gas until the end of M. Liquid is during the middle line segment L. At what temperature does the substance condense? So even though it's boiling or vaporizing, the point in which it boils is also the point in which it condenses. The point at which something melts is the same point in which it freezes. So even though this is something that's being heated up, we actually know what temperature it condenses because it's going to be the same as the boiling point, 200 degrees Celsius. So which segment shows the heat of fusion of energy? It would be K. So heat of fusion is the heat that's going to be released during melting, or heat that's absorbed during freezing. I said that backward. Heat of fusion is released when it melts. It's released when it freezes. It's absorbed when it melts because it's getting hotter. You're adding heat to melt it, so it's gaining heat when it melts. And what is the melting point? 0 degrees Celsius. Does this make sense now? So again, when giving graphs like this, flat portions refer to your phase change. We can identify where the solid, liquid, and gas is because solids are at the lowest temperature, gases are at the higher temperatures, and liquids are somewhere in the middle, or always in the middle. Again, I'm not going to really be testing this time over heat of fusion. You don't need to know that. But the test does have a graph like this. You should be able to look at it, identify where the gas section, what phase change is occurring between B and C, between D and E, identify information off of it. Does everyone feel comfortable doing this? So let's do another example. This won't work out. I'll call this A, this B, this C, this D, this E, and this is F. Alright, and I'll label here 5, here 10, there 12, this 30, and that 45. And these are minutes. Alright. So recall, so you should know that flat portions refer to phase changings. Flat refers to phase change. Sloped lines are single phase. So this is sloped. The lowest temperature line, sloped line, is solid. Highest temperature sloped line is gas. So looking at this graph here, this is sloped. The temperature is changing. This means this is solid. This sloped line has the highest temperature. It's 250 to 200. This is 180 down to make that 50. Just randomly guessing numbers. So this is a higher temperature. This must be gas. And this sloped line must be liquid. So A to B is gas. From B to C is condensing. So condensing. From C to D is when it's liquid. And from D to E is going from a liquid to a solid. Liquid to a solid would be melting. And from E to F is your solid. We can figure out the boiling or condensation point. So boiling point is the same thing. So boiling point equals condensation point. So we're looking at condensation. That'd be 200 degrees Celsius. So it boils at 200 degrees, or it condensates at 200 degrees Celsius. Melting point equals freezing point. You can see it freezes at 180 degrees Celsius. That's really, we can see that in here, it took it took 5 minutes to go from a gas to a liquid. And that's basically all you do. The most important thing is being able to look and identify these. So solids are going to be the slope line at the bottom. Flat lines are either going to be melting, freezing, boiling, condensating, vaporization. So heating curve of water. Water water is matter that can go through all the different phases. So if we're adding heat energy in a positive direction, it starts out as a solid, and the solid warms up. This is another way you can think of it. So we start out with a solid, and we're heating it up. So temperature is increasing. So as we warm up the solid, it'll eventually start melting and then it's going to all melt and then become a liquid. Then we start warming up the liquid. The temperature is increasing until we reach the boiling point. When it reaches the boiling point, it's going to start boiling until it all becomes a gas, and then we're going to start heating up the gas. We can go in reverse. We can start cooling a gas down until it reaches the boiling or condensation point, at which point it's going to condense down into a liquid. Once we're a liquid, if we keep removing heat energy or keep reducing the temperature, the liquid's going to cool until it reaches the freezing or melting point, in which case it's going to start freezing and turning back into a solid. The key things are there is no temperature change during a change of phase. So the flat portions, this uses the British spelling, they had a U in it. But there is no temperature change during a phase change. So the flat portions are phase changes. The slopes we can see are the different phases. So what is the phase change called from B to C? Melting. Let's see. So I wanted to look at the answers at the same time. So melting, correct. Which letter represents a gas? Which letters? E to F. Oh, I thought you said B to F. Yeah, E to F. What is the phase change from D to E? Boiling or vaporization. Which letters represent a solid? A to B. What is the phase change from E to D? Yes. So notice the order. It says going from E to D. So we're going in reverse. So do you pay attention as I like giving a lot of trick questions? What about C to B? So going in reverse. Freezing. What is the temperature change when a phase change occurs? It doesn't change. So there is no change. Oh no. My printer is not working on my computer. He said that? Mm-hmm. So, I don't have a PowerPoint over this, but this is something called a phase diagram. So this is for water. It's very technical because water is very well studied. So this line right here. So at 1 atmosphere, we know that water freezes at 0 degrees Celsius, and it boils at 100 degrees Celsius. Now, let's say that we go up to Colorado. So let's say, let's do Mount Everest. Mount Everest pressure in kilopascal. No, let's do in Mount Everest instead. It's slightly over 30 kilopascal. So this is logarithmic. Notice that when I go from here to here, it goes from 10 to 100. So this is 90 difference. This is 9. So this goes from 1 to 10. Have y'all ever seen logarithmic scale? So every line is a factor of 10. So I going from here to here is 10 times. Going here to here is 10. Going here to here is 10, 10, 10. So this is logarithmic. So to find 30 kilopascal is 1, 2, right here. So right here, if you're at the top of Mount Everest, water would freeze at about 0 degrees Celsius. But look at what temperature it'll boil at. It'll boil at about 75 degrees Celsius. Yes. So let's look at the pressure. Pressure of water at... Okay. What's the deepest pressure at bottom of... Yeah. In kilopascal. So it is 10 to the 8. So to do that in kilo, that'd be 10 to the 5. So that's 10,000. So 10 to the 8 Pascal and megapascal. So 10 to the 8. So that's 100. So in the bottom of the ocean, it's still a liquid. It's right here. So at the bottom of Mariana Trench, it's as long as the temperature. Actually, the temperature can get down to about negative 20 and still be liquid. At the bottom of Mariana Trench. It can't become a gas. So even if you heated it up, so near the volcanoes, underwater, it remains a liquid all the way up into. Actually, it's always a liquid. Water can't exist as a gas at Mariana Trench levels. So I want to point out two major points in these diagrams. This point right here is called the triple point. I don't think I really need to clean my vacuum chamber. But how much time do we have? None. I'll continue tomorrow. Here's the code word. No, it can't be a gas at that pressure. It can be frozen. This line continues. So this only goes up to like 400 degrees Celsius. So this continues upward. Actually, I can tell you right here it's a liquid. I think so. Maybe I'm wrong. No. We test these in the lab. We can create these pressures in a lab. But pressures like this can be generated near the core of Jupiter. In which case, not 1 terapascal. So if you go way into Jupiter's core, it's actually liquid, or no, it's like liquid hydrogen or metallic hydrogen. It no longer acts like a liquid or a metal, and the hydrogen becomes a metal almost. Because the pressures in Jupiter near the core is extreme.